Okay, I tested the BigBlueBiTT here with 21.1 volts input, and I put up a video just doing resistive Ohm's law with knowing the voltage over the resistor. And I have two resistors, one for each secondary now. And that came to 703. That's this one here. Input. Output is one of these, 0.12. The other one's 0.579. You add them up is 0.703. So that's pretty good. However, I went and checked it with a scope, what's coming out. The amperage, 0.01 squared divisions. Here's what it looks like on a scope. The taller ones is the volts, and the others the current. And so here it all is, if you want to look at all this. It came to just about the same as what the resistive load was using Ohm's law, voltage squared divided by resistance. And so here's what it came to with a scope. .134 instead of 0.124 watts, and then 0.627 instead of 0.579. So here's the difference. It's pretty much the same. One is Ohm's law, this one, and this is what the scope says. So that's all good. So, but the scope does bring it up to 0.76 instead of 0.70. So whatever. So it's around there. The output. Now the input is the other question. I saw a video by Karl Heinz, done in Ottawa, 2019. And he had a phase angle on the input. And Jerry's been telling me I should check my input. And so apparently you should have a isolation transformer before the Variac, because it's kind of connected right to the grid. And if anybody messed up the ground, you can get electrocuted putting a scope right on the grid line, right, coming straight from the Variac. But I did it anyways. I risked my life. So, and this is what it looks like coming out. And a little bit, I'll show you a nice bit map I did showing everything clear. What I did is I put it in this setting, which is 10 milliseconds. Because it was a little bit clearer to see the phase shift here. But there is a phase shift because the peaks don't line up. The voltage is the taller one, and that's a little bit to the left of the current, which is the smaller one. So there's definitely a phase shift on the input, which is good because that means that you figure out the cosine and you times it after you get the volts and amps. You times it by the cosine, which is 0.39 once you know the phase angle. So it reduced the input watts from, because now that you're looking at the phase angle, the meter just does the volts and the amps. But when you include the phase angle, you know, like when the amps and volts are not lined up and there's a shift, you get to include the 0.39 at the end of it. So it brought it down to 0.15 input. 0.15 watts input. And so let me show you this over here. This is my computer, so I put it into a paint program. The picture, the scope you just saw. And right here, there's a phase shift there. And that looks like about 1.5 spaces. But it's kind of blurry, and it's at a steep angle going up here. So what I did was, knowing that it's at least one space, so I went to the peaks. Here's the peak there, and there's the peak there. So that between those two, I figure that's 1.2 spaces. And that's the phase angle. And if you go for one 360-degree cycle, you know, one AC cycle, that comes to 6.75 spaces. You can count them. So you go 360 divided by 6.75 is 53.3 degrees per space. And we know it's 1.2 spaces for the phase shift, so there it is. That's the phase angle. 63.9, which is like 64, I guess. And that is cosine 0.39. So when you figure out the watts, it's 18.7 times 0.021 amps is 0.392, which is like almost what I got with a meter. Meter was 0.442, 422 or something. But the cosine, because there's a phase shift. Because, you know, the grid's coming in and it hits an inductor. So you have a phase shift. And it's a 12.8 ohm inductor. So here is the watts input now. And if you want to see my math here it is. No big deal. Square divisions, you know, each square has 5 spaces in it. So at 20 volts, it's 4 volts per space. And the amps is set at 0.01 volts. And so it's a 0.002 volts per space. So here's the voltage. From there to there, peak to peak, 13.25 spaces vertical. And there's the amps, 3 spaces, and I went right in the middle of the sine wave. So anyways, so knowing all that, 13, so you get that. 53 volts peak to peak divided by 2's 26.5 times 0.707 gives you RMS, and that's what the volts is according to the scope. So on the meter it said 21.1, but the scope says 18.7, you know. That's just what it is. And the amps, is, there it is, peak to peak, 0.006 divided by 2, blah, 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 0.07, and then I'm using a 0.00. There's a mistake. It's a 0.1 shunt, not 0.01. I have a 0.1 resistor there, so I need to change that. So anyways, it comes to 0.021 amps, which is just what I measured with a meter coming in. And then you get to do the cosine, and there it is. 100.152 watts input. That's not bad considering output is 0.76. So there's that. Okay, thanks for watching.